Hi viewers of Electronics Class Tanzania. Welcome to lesson 7. Your coach Engineer Mhina will teach you today about improving stability of the transistor by using an emitter resistor. In the previous lesson, in lesson 6, we learned about operating mode of a transistor, and we've seen how transistor can operate in a active mode, saturation mode, and a cutoff mode. But basically, we learned that a transistor should operate in an active mode because we need the shape of the input signal to be the same as the output signal. So the shape should be the same, no distortion. But in a saturation case, we have those distortions. And today, in lesson 7, we'll learn about how an emitter resistor can improve stability in a transistor. Yeah, today's lesson is improving stability of a transistor by using emitter resistor. We'll see two scenarios. The first scenario, we'll see a biasing circuit transistor without an emitter resistor, and we'll have our values. And then a second scenario, we'll have a biasing circuit transistor with an emitter resistor. But also, we'll be using two different beta, a beta at 100 and a beta at 50. So let's have our circuit here. This is an NPN transistor. NPN transistor, the arrow is outward. This common emitter, we ground here. We have our RB here, and also we have our RC here. This is a biasing circuit. It's a DC with RC. Let's put our values. RC is 2 kilo ohm. RB is 250 kilo ohms. We don't have a emitter resistor here. So we'll find the values and see how, in a second case, we'll put a resistor and see how the stability of a transistor will be. So this is a silicon transistor, and a silicon transistor VBE is equal to 0.7 volts. So we have to find IB, we have to find IC, and we have to find the VCE. So the formula of IB from this circuit, IB is equal to, we have VCC here. We have VCC here, our source. Can show also like this one. It's positive, negative. We have VCC here, which is 10 volts. So, according to our circuit here, VCC minus VBE over RB, this is just Ohm's law. We have our IB, VCC, VBE, this one, drop, this is drop. Then we have IB here, IB current, IB. This IB current, and the VBE is this one. So VCC is 10 minus VBE is 0.7 over RB is 250, but times 10 power 3 because it is in kilo ohms. It's in kilo ohms. So our IB is equal to, we'll just use a calculator here. Just use a calculator, 9.3 over 250. This will be milliampere. By using just simple calculator, 9.3 divided by 250, we have 0.0372 milliampere. This is our IB. So we have to look for IC, which is equal to beta IB. And we said we will use beta at 100, and also we'll use another scenario at beta at 50. So in this case, beta is 100 times IB, which is 0.0372 equals to 3.72 milliampere. That IC. So we have to look for VCE. VCE is equal to, this is just using Kirchhoff's voltage law. We use Kirchhoff's voltage law. We'll use that one. This is Kirchhoff voltage law. So VCE is equal to VCC minus IC RC here. And this is the VCE, this one. So VCC is 10. It's 10 minus IC. IC this one, 3.72 milliampere. So it's 10 power minus 3 times RC is 2 kilo ohms. It's 2 times 10 power 3 to get ohms. So this is cancelling each other. So again, with a normal calculator, we take a 3.72 times 2. 3.72 times 2. 3.72 times 2. We have here 7.44. And here we have 10. So if we minus 10, we get 2.56. So our VCE is equal to 2.56 volts. So we'll put these data here. So because we are going to use them in a table to show the comparison. So the scenario at beta 100, we have IB equal to, our IB is here, is 0.0372, and IC equal to 3.72. These are milliamps, and our VCE is equal to 2.56 volts. These data will use them again. Let's continue with beta at 50. So we need to find IB. Again, IB is equal to VCC minus VBE over RB. Our VCC is 10 minus VBE is 0.7 of RB is 250 times 10 power 3. Again, IB, our IB here is just simple algebra. Our IB will be the same like the former one, 0.372. This is IB. So we have to look for IC. IC is equal to beta IB is equal to beta is 50 now times 0.0372. Now it's just simple algebra. By using our calculator, we take 50 times 0.0372. We have 1.86 milliampere. This is milliampere. So we have to find again VCE by using we use Kirchhoff's voltage law. On this side, VCE is equal to VCC minus IC RC, which is 10 minus IC. IC is 1.86 milliampere, 10 to the power minus 3, times RC is 2 kilo ohms, which is 10 to the power 3. These are cancelling each other. Then just it's a normal algebra here. By using a calculator, we'll see how much we have. 1.86 times 2 is equal here is equal to 3.72. We minus by 10. We have 6.28 volts. This is our VCE. So again, I'm putting my data here. At beta at 50, IB is the same, 0.0372. This is a milliampere. Our IC at beta at 50, our IC here is equal to 1.86 milliampere. And also our VCE is 6.28 volts. Here it's beta at 50 and here beta at 800. So let's continue with the second scenario, whereby our biasing transistor circuit has got a emitter resistor for improving stability. Again, we have our NPN transistor. This NPN transistor. The arrow is outside. Now we have what we are talking about is this RE emitter resistor for improving stability, but we'll have the data which will prove that. Then we have our RB here, and then we have our RC here. This is the VCC. This is RB, and this is RC. This is collector resistor, base resistor, emitter resistor. This is our transistor here. So let's put the values. Our RC here is 2 kilo ohms. Our RE here is 1 kilo ohm. Our RB here is 250 kilo ohms. Since it's a silicon transistor, the VBE, base emitter voltage, is 0.7 volts. And also will go the same way like the previous one. We'll use beta 100, and again we'll use beta at 50. Then we'll keep the data and we'll have a table. So our IB from the circuit, our IB is equal to VCC minus VBE over RB plus 1 plus beta RE, because now we have RE. So now we have to put the values. Our VCC is 10 minus VBE is 0.7. Our VBE is here. And our RB is 250. This is kilo ohms plus beta is 100. So 100 plus 1 is 101. And our RE here is 1 kilo ohms. So it's also 10 power 3. 1 kilo ohm. So again, it's just using calculators. 10 minus 0.7 is 9.3 over. Here, it's just a plus. 250 plus 101. We have 351 times 10 power 3. And when we take our calculator with this simple algebra, is 9.3 minus 351. We got here 0.0264 milliampere. Then we have to look for IC, which is beta IB. So our beta here is 50. Is 100. Our beta here is 100. It's first scenario. Times IB, which is this one, 0.0264, which is equal to 2.64 milliampere. This is our IC. Then, by using Kirchhoff's voltage law, this is Kirchhoff's voltage law, we'll use that. So, VCE is equal to VCC minus IC RC. This one also will minus this one, IE RE. We know that IE is equal to IB plus IC. So, VCC is 10 minus ICRC. We have IC 2.64 times RC. This is the milli, 10 power minus 3. RC is 2 times 10 power 3 is kilo ohms minus. So we have to sum up here. So we can have IE, which is equal to IB. IB is this one, 0.0264 plus our IC, 2.64 equals to. So it's again our normal calculator is a simple algebra. 0.0264 plus 2.64. We have here. I'll put here 2.6664. So this is our IE. So our IE is 2.6664 times 1 times 10 power 3. That's our kilo ohms RE. This cancel each other, and we have now, this is 10 power, this is just this kilo ohms, but this one is milli, this is 1 milliampere. So we have here also times 10 power minus 3. So this one will cancel each other. Again, by using just a normal algebra here, we take 2.64 times 2. Here we have 5.28 minus that one, 2.6664. So we take 5.28. Okay, if we plus 2.6664 and then we minus by 10, we have our VCE, which is 2.05054. Yeah, 0.054 volts. This is our VCE here. So we'll keep these data because we are going to use them. We'll put a table there. We'll use them. So I'm going to have a space here so that I can keep this data. Okay. I'll keep them here. So this is another scenario which we have a meter resistor. My beta at 100, my IB is equal to, my IB is this one, is 0.0264. This is a milliampere. My IC is equal to, this is my IC, 2.64 milliampere. And my VCE is equal to, this is my VCE is equal to 2.054 volts. These are my datas. So let's go to another scenario when beta is 50. Let's see IB, IC, and the VC, VCE. When our beta is 50, so we are looking for IB at beta at 50. VCC the same is 10. VBE is 0.7 over RB is 250 times 10 power 3 plus our beta is 50, so we have 50 plus 1, we have 51 times 1 RE, which 1 times 10 power 3 is 1 kilo ohm. So again, we'll have our normal algebra 9.3 over 250 plus 51, because this will be outside the bracket. So we have 3, 0, 0, 1. So just normal algebra by using our calculator. 9.3. When you take 9.3, you divide by 301. You have here 0.0308 milliampere. 308 our IB. So we have to look also for our IC, which is beta IB, equal to normal algebra 50 times 0.0308, which is equal to, by using a calculator again, 50 times 0.0308, we have here 1.54 milliampere. This is our IC. We have to look for VCB, VCE. Then by using again Kirchhoff's voltage law, VCE is equal to VCC minus IC RC minus IE RE, and we know, just use this space, VCE is equal to VCC minus IC RC minus IE RE. VCC is 10 minus IC. Our IC here is 1.54 times RC is 2 times 10 power 3 minus our IE. Our IE is equal to IB plus IC, which is equal to, we have our IB here is 0.0308 plus our IC here is 1.54. So we have our IE. Again, simple algebra, you can use a calculator. 0.0308 plus 1.54. We have here 1.57. This is our IE, 1.57 milliampere. So this is at no resistor emitter. So when we put the second scenario with the circuit with the emitter resistor, now we put emitter resistor. So let's see the datas. We have beta here, we have IB here, we have IC here, we have VCE here. So our beta at 100, our IB at 100, our IB was 0.0264, and our IC is 2.64, and our VCE is 2.054 volts. Beta at 50. Beta at 50, we have our IB 0.0308 and our IC 1.54, and our VCE is 5.35 volts. So the first table is without emitter resistor, but the second table with the emitter resistor. So the comparison, will see the percentage change in a collector current will be higher when with no resistor emitter, but with the case with the emitter resistor, the percentage of collector current will be small. We can check here the percentage. Let's take, we are doing this one. We are comparing, then we'll compare this one. This is our collector current. Then we will take 3.72 minus 1.86 over 3.72 times 100. Then we will have our percentage here. Again, it's a normal algebra here. When you take 3.72 minus 1.86, okay, and is equal to we get 1.86 over 3.72 times 100. So when we take that 1.86 divide by 3.72 times 100, we have 50%. We have 50% here. Take a look here when we introduce a emitter resistor. Likewise, 2.64 minus 1.54 over 2.64. How much percent we have here? Of course, times 100. A normal calculator, 2.64 minus 1.54, get 1.1. 1.1 divided by 2.64, we get here 41%. So we can see here, without emitter resistor, the higher the percentage, but with introducing emitter resistor, the lesser the percentage. And when you increase the emitter resistor, also the percentage is decreasing. So in comparison, the same applies to collector emitter voltage and collector emitter, yes, collector emitter voltage at no resistor at emitter, and collector emitter voltage at with the emitter resistor. So in comparison with these two, two table, we've compared the percentage change of collector current, the percentage of the collector current, also collector emitter voltage, yeah, is much lesser. The percentage is much lesser, is much less when we are using a emitter resistor in this biasing transistor circuit. This is our conclusion, and we've seen the data from two tables that when you introduce a emitter resistor, the percentage of change of collector current and also the percentage change of collector emitter voltage is becoming much lesser, and the higher the emitter resistor, the less the percentage. So this is how we are improving stability of a transistor by using emitter resistor. So the analysis shows how we can improve the stability of a transistor by using emitter resistor. Hi viewers of Electronics Class Tanzania, we learned today in lesson 7 about how the emitter resistor can stabilize the bias circuit of an NPN transistors. According to the data we had and the table, we've seen that before introducing emitter resistor, the percentage change of the collector current was 50, but after introducing 1 kilo ohm of the emitter resistor, the percentage change of the collector current decreased to the 40%. And also, when you increase the emitter resistor, also the percentage change of the collector current will be decreasing. Also, the collector emitter voltage will be decreasing, as we have seen in the data here in today's lesson. So don't miss next week for Electronics Class Tanzania. We'll be learning about transistors, and this is a elementary level, but we'll be progressing step by step. So don't forget to like, share, and comment, so many we can learn Electronics Class Tanzania.